So we're presenting a comparative study of different optimization methods. So the objectives of our presentation are to be able to optimize convex functions. We also want to find the function that best fits a set of points, and we are also able to minimize the cost of the process given different variables. So something that's useful for different production methods, etc. So I don't know if anyone wants me to go over convexity to explain sort of what that is and why that would be important for optimization.
Maybe you can say a couple of words.
Okay, so I'm gonna try to draw on the screen, although I'm not very good. But so the idea is that so we can have a convex set, which is a set where for any this is for any two sorry. So we have a set, for example, this one, where we can take any 2 points inside the set, and every point between these two will be within the set, right? So formally, if we take 2 points x, hopefully you can read what I'm writing, on a set omega, then for all lambdas between sorry 0 and 1, then lambda x plus 1 minus lambda y is within the set omega. Yeah. Okay, so then what we're working with here is, so that works for constraint sets, etc. So what we're working with is convex functions. So we can have a function such as this one. And so we want to take any two points on the curve. And so if we draw a line between them, the line itself, so any point on the line, will be above its corresponding point on the function. So so if we take x, y, then we can say that, let me think. Yeah. So for any x, y belonging to, yeah, I mean, in R, since our function, so we have f of x, which maps R to R, right? So then if we take lambda of f of x plus 1 minus lambda of f of y, it'll be greater than or equal to f of lambda x plus 1 minus lambda y. So that's just a formal way of saying that this point is below the line between f of x and y. Okay, so in our presentation, we're, sorry, I can't. This here. Sorry, I'm stuck on page now. Okay. Yeah. So we're going to present 4 different optimization methods. So firstly, gradient descent, which is the most basic, then Newton's method, coordinate descent, and golden section. So golden section is a bit different, and we've also created a version of it adapted for multiple variables. And then we present a sort of comparison of the efficiency of the different methods and a conclusion on which cases to use them in. So Karim's going to begin by presenting the first 2.
So gradient descent, or the steepest descent method, is a first order iterative optimization algorithm to find the local minimum. Over every iteration, we step predefined or using line search towards the direction of the steepest descent, or where the derivative is the greatest. We use the equation that's on the board, the a(n+1). And this equation implies that for every, say we start at a point an, the point f of an+1 will always be smaller, as we are moving against the gradient and therefore towards the minimum.
I'm not sure. I probably depends a little bit on how lucky we are. Is it really true that f of an+1 will always be smaller than f of an?
For a gamma, so for a step size that's small enough, yes.
I mean, but small enough depending on the function, right? So
yeah.
In principle, that's our hope. But as far as I understand, that may happen or may not happen, right?
Yeah.
So we're going to present, he's going to introduce a method for doing that after.
So that, which ideally like also brings us, also always brings the next points lower than our current point. But yeah, you're right by saying that that a certain gamma will not always bring us to a lower point. Okay, so however this this optimization problem may lead us to another issue, as we don't really know how big of a step size we need to take. If the step size is too large, the program will never converge. And on the other hand, if the step size is too small, it will take very long, or at least longer, to find an optimal point. So either we can test out different step sizes, aka learning rates, to see which one would be the most effective, or a better way would be using line search. Line search basically looks around a point to see how big of a step it can take, so that the function is reduced to the most. It does this by following Wolf conditions, which are sets of inequalities which it tries to minimize, as you see on the board. So just to explain a bit of the variables in these inequalities. So generally, C1 will always be greater than the, wait, let me just see so it's more obvious for you. So C1 is always greater than 0. C2 will always be greater than C1. And C2 will always be smaller than 1. C1 is usually chosen to be quite small, whereas C2 is much larger. For example, for Newton or quasi-Newton methods, which are methods which find minimas, maximas, and zeros, the C1 is usually equal to 10 to the minus 4, and with a C2 being equal to 0.9. But again, this is just convention. To elaborate on the inequalities, the condition of I, also called Armijo rule, ensures that the step length decreases f sufficiently. And 2I, or curvature condition, ensures that the slope has been reduced sufficiently. These conditions can be interpreted as giving us a range of possible acceptable step lengths for our algorithm to take.
Yeah. Good.
So our next optimization method is called Newton's method. The Newton's method for optimization is a second order iterative optimization algorithm that can find a minima, a maxima, or a saddle point of a function. To deeper understand this iterative method, we must go through single real variable functions, which will allow us to consider and understand the more general multivariate case later. So if we consider a twice differentiable function f that maps R to R to solve, We will start with an initial random point, initial random guess of x0 that will converge to a point, to an optimal point x star by using a sequence of second order Taylor approximations of f around the iterates. We define the next iterate, xk plus 1, being equal to xk plus t. If the second derivative is positive, then the quadratic approximation is a convex function of t, and its minimum is found by setting its derivative equal to 0. Therefore, if we follow these steps, we get our final equation for the next iterate. To convert this to higher dimensions, we must simply replace the derivative with the gradient. So, Henry, next slide. The derivative with the gradient, the reciprocal of the second derivative with the inverse of the Hessian. We can also include a step between 0 and 1, as you see in the final equations, the second final equation. This is done to ensure that the Wolfe conditions are satisfied at each step of the method. For step sizes other than 1, the method can also be referred to as relaxed or damped Newton's method. All this shall conclude our Newton's method section with the following equations. The x plus 1 without the gamma, and so the basic is of the Newton's method, and the dampened Newton's method at the bottom.
Okay, so since we were primarily focusing on computing, we decided to cover coordinate descent, which is the method that we can use when computing the entire gradient is too computationally complex to do in a single time. So what we do instead is we iterate over all the different dimensions of the function, so n dimensions, and we calculate the partial derivative on that dimension. So here we're assuming gradient descent, so this can be done with different methods, as we'll see later. But so we calculate the partial derivative of the function for that dimension, and we optimize over that dimension the variable. So here in our diagram, you can see that it takes sort of like steps in a zigzag towards the lowest point as we optimize each dimension. So that's probably the most simple one. And so moving on to, my thing is stuck again. Okay, sorry. So moving on to golden section, which is slightly different than the other ones we've studied in our presentation. So this applies to non-differentiable continuous functions. And so it works inside a specified interval. So we can't study the entire function at once unless we choose, well, we can't, but we can choose a very large interval to study. So what we do is we define R, which is phi, the golden ratio, -1, and C, which is 1 minus R. And we choose two sections, x2 and x3, in a ratio of R to C and C to R.
Could you recall phi? What is it? 1 plus square root of 5 over 2? Or
Yes.
Right? Okay.
Okay. So we have these two sections, and then we calculate f of x2 and f of x3. And depending on which one is larger, so let's say x3 is larger, then we reduce on this side. So x4 becomes x3, and we recalculate sections based on those new variables. And then so to end the optimization, so when we decide that we are close enough to the optimal point is when x1 and x4, so the interval becomes small enough that we consider it negligible. So this only applies to single dimensional functions, but my thing didn't get stuck all the time. We've adapted it to multiple dimensions. So I've got this slightly confusing diagram, but so what we've done is we've chosen a sort of an area in the n dimensions. So in this case, it's 2, but this can be used in any dimension. And so we kind of use coordinate descent in the sense that we optimize one dimension at a time. But because if we keep the interval at a small, we keep a very small interval at each section, at each iteration, it'll get stuck at that point. So at each iteration, we reset the interval for that dimension. So these black lines sort of represent the interval that we're optimizing over for that dimension, if that's clear.
No, not quite. So could you say again? So we first do, say, suppose we optimized, I don't know, X. Now we found some point which is whatever, considered optimal. Then what?
Okay, so we've got this interval for both dimensions. So we first optimize over this one dimension and we find this red dot, which is the optimal point.
Mm-hmm.
We then switch to the next dimension, for which we find this point. And then because we don't want to keep the same interval, because it would just get stuck here, we reset the two ends of the interval to find a new optimal point for that dimension. And then so it ends up getting to the minimum point for the entire function.
Mm-hmm. Okay.
And then so to the termination condition, so for each dimension, we keep the same one as previously, but what we do is we take the entirety of the previous x and we calculate the norm of, we subtract the current x from it. And when the norm of that is lower than a certain value, then we stop optimizing. So essentially when it's sort of an approximation of the gradient, but for a non-differentiable function. Okay, so now we are going to present what we found when comparing them. So, Karim, I don't know if you want to go over the code that we wrote.
Yeah.
Okay.
Interesting.
So you can go over yours.
So the gradient descent and Newton's method, they're not very far theory. So we first have to define a stopping condition, which is simply when the gradient of the point that we're at is close enough to 0. So we can choose this precision. The precision, yeah. Sorry. So for example, here the precision we chose is 10 to the power of -6. So the step size here for the gradient descent, we used the line search. We didn't use the specific lines, specific step size, because the line search will find the biggest step for us, which for our example was more useful. And then we used the same iterative method that I explained before by multiplying the gradient with the step size, which will eventually get us to the lowest point. So for the Newton's method, it's approximately the same thing, but instead of going down by the gradient, we went down by the gradient divided by the Hessian, which will eventually take us to a point where the gradient is so close to 0 that it's as if we're not actually moving down, like lower. So we found the optimal point.
Okay, so again, the coordinate descent isn't really anything special. So we just iterate over every dimension individually here, and then we apply gradient descent to that dimension. So moving on to golden section, it's slightly more complex. So what we first do is we store the initial sections So that's so that we can reset the intervals that we're optimizing over. And we store a place. Is that me or who's annotate? Okay. So we then store a placeholder value for the previous values to so that we can fulfill this this stopping condition, and we then define the new sections. So what we then do is we calculate, we iterate over each dimension here, and then we optimize we optimize with those new sections for that single dimension. So what we then did is we generated pseudo-random data, which correlates. Karim.
What are those pseudo-random curves that?
Sorry, and then so what we did was we applied ridge regression. So ridge regression is fairly simple. It's just a quadratic. It's just a quadratic regression equation. So we essentially find the. Can someone stop? Anyway, so we find the the variables which will best multiply with the data that we have to give an output that's desired, and we also account for the norm of the variables. So what we then did is we applied this for every dimension from 1 dimension up to 90 dimensions. And we graphed the time taken to reach an optimal point and the total steps taken to reach an optimal point. And so what we present here is that in purple, we have the coordinate descent, which is misleading because we would say here that it's the slowest and the one that takes the most steps. But in terms of the computational complexity, so the amount of resources we need to calculate each step is much lower. So in terms of computing, it would possibly be the only usable method to achieve what we want. So then in yellow, we have the golden section, which is slower, and so this is sort of what we would expect because it's not using any, it's not really specific to the function, but it has the advantage of not requiring a differentiable function. So I think that one sort of sets itself apart in the sense that it can optimize any function that we give it as long as it's continuous as opposed to the others. And then the bottom two in blue and red, we have Newton's method and gradient descent. So as we can see, these are the most efficient in lower dimensions, but I think that this doesn't really demonstrate the amount of resources required for each. And so Newton's method, we are essentially solving for the Taylor expansion of the function, right? And so since we're using quadratic regression, it's sort of solving itself since the Taylor expansion is quadratic. So that's why in this specific case, it solves so fast for itself. So that's sort of why we expect these results. And yeah. And then just to conclude, this can be applied to all sorts of things. So for us, it was specifically neural networks, and it can be applied to much more complex functions, especially the gradient descent using the chain rule and stuff like, so often they'll get stuck in local minimums because that's where the gradient will be 0. And so we can add stuff like momentum so that they'll keep going in that direction afterwards. And that's our presentation.
Okay.
thank you very much.
Okay, thanks a lot. Any questions?
Maybe, what was your motivation to work on this at the beginning, and what did it bring to you, mathematically speaking?
Yeah, so what we wanted, so we were personally already working on artificial intelligence and neural networks specifically. So we sort of wanted to understand more in depth the methods that we use to optimize these. So in that case, it's like specifically gradient descent for the most part and improvements on that. But this sort of gave us a larger picture on the applications of the technology and the mathematical basis for it.
Small question. I myself also did a bit of machine learning, just some basics, not that much, but I know that gradient descent is widely used for machine learning. What about the others? I didn't hear much about the other. Like, are they also used much or not?
Yeah, so in terms of the others, so at this point in time, we don't really use any of the others in machine learning. Well, I can say for golden section, it's not the most efficient for differentiable functions. So neural networks are always differentiable. And so it wouldn't really make sense to sacrifice efficiency for that benefit. Then Newton's method, so it's not used because it would be essentially impossible to calculate the Hessian of such a complex function. And then,
well, yeah, but it would like just be computationally redundant.
Yeah.
Just to calculate the Hessian at each time, whereas we could just calculate the gradient for the gradient descent.
Makes sense.
So what we're sort of left with is gradient descent and like improvements. So for example, there's like Nesterov momentum and like adaptive movement.
Okay, interesting. I didn't know that. Like, you said that like neural networks are differentiable. I mean, this statement is just a bit, let's say, surprising.
Yeah, because it's like in the end, it's just like.
Yes, I know.
Yeah.
I mean, in the end, I can imagine it, but like the statement just as it is alone, without imagination, it sounds like. Yeah, surprising.
It's complex, yeah.
Okay, more questions? If not, thanks a lot.